Part 3, and hopefully the final one for 3.7, dealing with rates of change in the natural and social sciences. As I promised, I'm going to focus in this one particularly on particle motion problems, and I think I'm going to go ahead and just focus on 7, 9, and 10 from 3.7 in your book. I've already done 8. And so these will be a good way for us to get a handle on this, sort of give us a first view in terms of the application of derivatives as rates of change to the sciences, and that'll sort of give us a running start into related rates when we get there in 3.9, because related rates are indeed kind of a beast. They are, in my experience, one of the hardest things for students to get a firm grasp on. So I guess in that way, I may see a little bit of value in this 3.7 and 3.8 area as sort of a running start into that. But I digress. Let's go ahead and start on number 7. Like I said, if it's from your book, but if you don't have your book, I'll try to put all the relevant information down on the paper so that we can actually follow along. Now, number 7 reads like this: the height in meters of a projectile shot vertically upward from a point 2 meters above ground level with an initial velocity of 24.5 meters per second is. Okay. Well, we've been told. Now remember that height or position is negative 1/2 gt squared plus v naught t plus s naught. Now in this particular problem they actually give you a lot of this. Now if we're talking with meters, then g is negative 9.8 meters per second squared. We've been told that it was shot vertically from a point 2 meters above the ground, so we know s naught is 2. We've been told that the initial velocity is 24.5, so v naught is 24.5. Sorry, that's a terrible 24.5. 24.5. There we go. That looks a little better. And so the model that they actually give us, and they give it to us backwards. Why they do this, I really don't understand, but whatever. Winds up being that. 2 plus 24.5t minus 4.9t squared. And remember, this is in meters, okay, and seconds. So we'll keep that in mind for our answers to particular questions later. Now, it says find the velocity after 2 seconds and after 4 seconds. Well, in order to get the velocity at those particular points, we have to get the velocity in general. And we know that the velocity is just the derivative of the position function, or in this case, the height function. So that winds up being 24.5t, or no, the t goes away, sorry, minus 9.8t. So what we really need is we need h prime of 2, okay, and then h prime of 4. And of course, the cute little toys that I had they belonged to the school, and therefore you're going to have to give me a second in order to break out a calculator. Since I'm just kind of can't be bothered to do it in my head right now. When we plug that in, we're going to get 24.5 minus, and that would be 9.8 would be 19, times 2 would be 19.6, which gives us 4.9. Now at 4 seconds, I know that 9.8 times 4 is going to be 39.2. Okay, so 24.5 minus that is 14.7 in the negative direction, right? So we have a positive velocity here. Obviously, by t is equal to 4, it has reached its zenith and has started to fall back to Earth. So we have a negative velocity at t is equal to 4. Okay, so I've answered part A, so kudos to me. Let's go ahead and make sure that those meters per second and meters per second. Let's go ahead and look at part B. When does the projectile reach its maximum height? Well, I know that it reaches its maximum height when I have a velocity of 0. Okay, so when I have a velocity of 0, I simply have to find my velocity function, which I have already found, 24.5 minus 9.8t, and I need to set it equal to 0. Okay, that means that t is equal to 24.5 divided by 9.8, 9.8, and that winds up being 2.5. Okay, so 2.5 seconds, right? Now that makes sense out of our first one, right? Because this is closer to 0 than this is. Because 2 is closer to 2.5 than 4 is, okay? So this is getting close to 2.5, so it's slowing down, and the velocity is actually getting rather close to 0. It actually is 0 at 2.5. Now, that is, because the question doesn't ask what the maximum height is, it asks when it reaches the maximum height. So we want to make sure that we answer the question, and we have. Because part C actually asks, what is the maximum height? Well, that means I need to take that 2.5, or 5 halves, and actually plug it back in to into the function. And that's easy enough to do. You have your calculators in front of you. I commend them to you. Go ahead and go nuts. All right. The other question is, when does it hit the ground? When does the particle hit the ground? Well, or what is it? Projectile is what I call it. Okay. When does it hit the ground? It hits the ground when the position is 0. Okay. So when the position function has an output of 0, that's when it hits the ground. And that's not calculus, guys. That's algebra 2, right? Now that may not factor nicely and neatly like we want it to. We can solve it by completing the square, or we can solve it by means of quadratic formula, but all you would need to do is just solve for t in this particular point. Now, the question then is, with what velocity does it hit the ground? Okay, well, whatever time this winds up right here saying, we then take this value and plug it into the velocity function, and I get 24.5 minus 9.8, whatever that value is, and that will be the velocity at which it hits the ground. I guess I need to go ahead and purchase myself a TI-84, don't I? I could get away with it up to this point, but I think the time is coming when I'm going to have to buckle down and actually purchase one. Alrighty, guys, let's go ahead and move on to the next question. The next question is number 9, because we've already done 8. Now 9 only has A and B, so let's go ahead and look at it. This is not a projectile, it's not a ball, it's a rock. So if a rock is thrown vertically upward from the surface of Mars with a velocity of 15 meters per second, its height after t seconds is, h is equal to 15t minus 1.86 t squared. Well, the reason for that is the fact that, we expect gravity to be different on Mars, okay? So it's going to have a different acceleration due to gravity, but whatever that acceleration is due to gravity is still g, okay? And therefore we still have the same general thing. It's negative 1 g, which is a constant, t squared, plus v naught t, plus, in this case, h naught, right? Okay. Well, it says, what is the velocity of the rock after 2 seconds? Well, the velocity, of course, is going to be the derivative of the position, and I get 15 minus 1.86 times 2, and that would be 3.72, 3.72 t. Okay, and then I simply need to evaluate it at 2. Okay, 15 minus 3.732 times 2 is 15 minus 7.44, which is going to be 7.56. Okay, that is the velocity of the rock after 2 seconds. So obviously after 2 seconds it's still going up. It has slowed down, but it still has a velocity of 7.56. Now, what is the velocity of the rock when its height, this is part B, what is the velocity of the rock when its height is 25 meters on its way up? Well, and then on its way down. Well, just like in part 7, we can expect that those are going, or actually that wasn't part 7, that was actually question number 8. Question number 8, when it said what is the velocity of the ball when it's 96 feet above the ground on its way up and on its way down, because of the symmetry of a parabola, and of course these are all modeled because they're gravity problems, they're all modeled with parabolas, then 25 meters on its way up and 25 meters on its way down should have velocities that are negatives of each other. But what I need to do first is I need to figure out what that time is. 1.86 t squared. So you solve for t, okay, and then both of those t values then get plugged into the velocity function, and you're done. Okay. Now I'm going to go ahead and, since I've explained it, I'm going to go ahead and sort of skip over that, since I don't have a whiz-bang calculator, and I'm going to, it's going to take me a little bit more time to do that, and I think I'd rather move on to 10 and try to squeeze 10 into this video as well. A particle, and this is number 10, a particle moves with the position function s is equal to t to the 4th minus 4t cubed minus 20t squared plus 20t, for t is greater than or equal to 0. See, this is one of those ones that is not a parabola anymore, and therefore algebra 2 methods of finding a maximum are not going to work. So we see a particle moves with position function s. At what time does the particle have a velocity of 20 meters per second? Well, in order to find the velocity, we simply have to differentiate the position function, and that's 4t cubed minus 12t squared minus 40t plus 20. And it asks, at what time does the particle have a velocity of 20 meters per second? You're like, well, that's a cubic. Well, they gave you 20 for a good reason. Okay, they gave you 20 because when you do that, those cancel out, and you're left with something that you can actually factor, right? Let's go ahead and factor out a 4t, and that winds up being t squared minus 3t minus 10, which further factors into t minus 5 and t plus 2. Now, the t plus 2 doesn't really matter because that's going to give us a negative t value, and we've already stipulated that t is greater than or equal to 0. So we know that at t is equal to 0 and at t is equal to 5, the velocity is equal to 20 meters per second. Okay? All you had to do is you had to get the velocity function by taking the derivative of the position function, and after that just recognize that what was really being asked was an output question for that velocity function, right? When is the rate of change, when is the velocity equal to 20? So you set the velocity function equal to 20, right? Now, in part B, it says, at what time is the acceleration 0? Okay, well, if the velocity function, sorry, I have to change sheets of paper. If the velocity function is 4t cubed minus 12t squared minus 40t plus 20, then the acceleration function, which we should know is the derivative of velocity, is 12t squared minus 24t minus 40. And it's asking, when is the acceleration 0? Well, that again is an output-based question. And we can set it equal to 0 and solve. We can go ahead and simplify this just a little bit by dividing through by 4. 6t minus 10 is equal to 0. Now, whether that factors or not, I'm really not concerned with right now. What I'm concerned with is the second part of the question, okay, because you know how to do that. That's just algebra. What is the significance of this value of t? Okay. Well, when the acceleration is equal to 0, it's possible that the velocity is changing sign. Okay, that the particle is no longer speeding up, it is now slowing down, right? Because when acceleration is positive, the velocity is changing positively. When it's negative, when the acceleration is negative, it means velocity is changing negatively, meaning that it's slowing down, okay? So when acceleration is 0, that is a possible point at which velocity is changing sign, okay? Going from accelerating to, you know, whatever the opposite of accelerating is. I know Williamson doesn't like decelerating, but you want to know what? I'm not a physics guy, so I can use the word. That's the significance of that point. And you need to get used to those questions. What is the meaning of that? What is the significance of that? Because those are the types of questions that are going to be asked on the AP exam. You're not just going to be asked to do things. You're going to be asked to interpret what you've done so that they know that you're not just a bunch of method monkeys, okay? I hope this has been helpful, guys. That is 3.7 in a nutshell. If you have any questions based upon what your teacher has assigned and what she has said that is different or distinct from what I have said, please do email me, and be on the lookout for 3.8. 3.8 has to do with calculus as it relates to growth and decay functions, and we'll get to that here in just a minute.